So let's start. So today's topic is about the Ampere's force, Gauss law for magnetism, Biot-Savart law, and Ampere's law. Okay. So we will start the Ampere's force. So let's start. Ampere's force is equal to magnetic field multiplied by current multiplied by the length of the wire. And here, as you can see here, the sine alpha is the angle between the magnetic field and the length of the wire. Okay, so if we have the such wire, which is the current I is carrying by wire I, and the length of the wire is equal to, let's say, L. Okay, so by using the left hand rule, we should find the force, which is the Ampere's force here. Okay, so is equal to here the magnetic field, the vector product of L multiplied by I. Okay, so according to the rule of the definition of the vector product, B, the vector product of L is equal to B multiplied by L multiplied by sine of theta. So here the theta is angle between the magnetic field and the length of the wire. Okay, so what else? By the way, here the F is force, and the unit of force, you know, the newtons. Okay, big N, and big B is here the magnetic field. And unit of the magnetic field is Tesla, big T. Okay, and L is here the length of the wire, and the unit of the length, as you know, meters. Okay, so what about the I? I is a current which carrying along the wire. Okay, so I is current, and the unit of current is ampere. Okay, so for example, example number 1. A wire of length L is equal to 1 meter carries a current of 10 amps perpendicular to the field of B is equal to 0.5 Tesla. Compute the magnitude of force on wire. Okay, so we have the a long wire like this. The length of the wire is equal to L. And here the L is equal to 1 meter. And the current is carrying in this direction. This is the current I. It is going to move in this way, okay? This one is the wire. And the I is equal to 10 amps. 10 amps. And this one is the perpendicular to the magnetic field of B, okay? It means that theta is here the 90 degrees and the magnetic field is equal to 0.5 Tesla. Okay, so we should find the magnitude of force on the wire, which is F, or let's call it the big F. Okay. So can you calculate this one, guys? I think yes. So force is equal to B multiplied by current multiplied by length of the wire and the sine of theta. So we have the B, I, L, and theta. So F force is equal to 0.5 Tesla multiplied by 1 meter multiplied by 10 amps multiplied by sine 90 degree. So the 0.5 multiplied by 1 is 0.5 and multiplied by 10 is a 5 multiplied by 1 here 5. So we have the 5 newtons. Okay, understand? Okay, the next one is about the magnetic flux. I think if I'm not make mistake, I don't make a mistake, we will see the electric flux, yes, but now we will see the magnetic flux, and they are the same means. So magnetic flux is BF, this one, P, okay? And the unit of magnetic flux is Webers, are just the W and B. So the number of magnetic field lines which passes through a section area A, so the magnetic flux is equal to F is equal to the integral of magnetic field dot product multiplied by the area dA. Okay, if here the magnetic field and area A are constant, so the magnetic flux is equal to B multiplied by A multiplied by cosine of theta. And there is a question of why here the cosine of theta? Because as I told you before, this one is the scalar product, okay, this one. So according to the scalar product, according to the R dot product, so B dot product, the A or just A is equal to B A cosine of theta. Okay, so theta is angle between the magnetic field and area. Okay. If here the angle, I'm sorry. So if here the area, let's say this is the small piece of area of the surface. Okay, this called is, let's say, dA, and magnetic field is going to move in this direction, and the angle between the area and magnetic field, let's say the 90 degree. It means that here the magnetic flux is equal to 0, because the cosine of 90 degree is equal to 0. So the magnetic flux is equal to 0 in this way. Okay. But if the area, if the surface, let's say this one's surface, and here the small piece of area is dA, and the magnetic field lines is the parallel to the surface, which is the magnetic field lines. If they are the parallel each other, it means that here the theta is 0, right? It means that we have here the maximum magnetic flux. For example, it means that the B multiplied by A multiplied by 1. This is the maximum. If the theta is equal to 90 degrees, we have the minimum magnetic flux, minimum. Okay. Which has the largest magnetic flux, A or B? It depends the amount of the magnetic field lines. If the magnetic field lines is more, it means that here the magnetic flux is bigger than others. Okay, so A is bigger than B here, because here the more magnetic field lines, and here the smaller than A. So Gauss law in magnetism. Gauss law in magnetism. We saw with you Gauss law in electricity, but now we will see Gauss law in magnetism. So Gauss law. For magnetism. If we have the such kind of surface, so this area is equal to A. This area is equal to A. And here we have the magnetic field lines is going to move in this way, okay? This way. And the Gauss law says that the number of lines entering a surface equals the number of lines leaving the surface. It means that the number of lines entering the surface, okay, this one, the number of magnetic field is going to up and is going to leaving this surface, okay? And if here the some magnetic field lines to the entering to the surface, it means that here the entering, let's say the N, and it means the entering to the surface line, to the surface lines. This is the N1. Let's call this one is N1, and N2 is the leaving from the surface. If they are the equals each other, N1 and N2 is equal to each other, it means that here the magnetic flux is equal to 0. Magnetic flux is equal to 0 here. So we have the such equation, the integral of magnetic field multiplied by dA is equal to 0. So this one is equal to, as we know, the magnetic flux. So magnetic flux is equal to 0 here. This one is the Gauss law in magnetism. And our last topic is about the Ampere's law. Ampere's law. Okay. What is Ampere's law? Ampere's law states that the line integral of magnetic field intensity around the closed path is equal to the sum of the current flowing through the surface bounded the path. We have here the new quantity H, which one is the magnetic field intensity here. So magnetic field is equal to mu0 multiplied by H. As you know, mu0 is the permeability of permeability, and the mu0 is equal to 4 pi multiplied 10 to the negative 7. Okay, and here the H is magnetic field intensity. Magnetic field intensity, and B, you know, the magnetic field. Magnetic field. And the Ampere's law says that if we have the such closed surface, let's say here there's some currents is going to inside of the surface, okay? Let's say this one is I1, and here we have the I2. Let's call this one I3. One is I4. So we have here the magnetic field lines, but we should say here the magnetic intensity. So magnetic intensity is equal to magnetic field divided by mu0, okay? So according to the Ampere's law, we have such kind of equations. The integral of magnetic field intensity multiply of the length of this area, this surface length of it means here dl, h multiplied by dl. Dl is the length of this one, okay, is equal to sum of the currents. So sum of the currents is equal to here what? I1 plus I2 plus I3 plus I4. I1 plus I2 plus I3 plus I4. Don't worry, we will see an example these ones, okay? Okay, and now is the last one is the Biot-Savart law. Ampere's law is not the last one, okay? So Biot-Savart law is what? So this law is used for computing the resultant magnetic field B at any position, okay? So we have, again, we have the wire, a long wire. Let's call length of the wire is L and the current is carrying in this direction, I, this one. And we should find the magnetic field at some distance from the wire. For example, here the R, in this point, we should find the magnetic field in this point, B. Okay, so we should use such equations to find the magnetic field. Okay, so the derivative of magnetic field dB is equal to here mu 0 divided by 4 pi multiplied by I dl sine of theta divided by r squared. But we need to find the B, not the derivative of B. So B, some distance r is here, dr is equal to mu 0 divided by 4 pi integral of I multiplied by dl vector product of unit vector of r divided by the unit vector of r cubed here. This one is the main equation of the magnetic field. Okay, so now we have some examples here. Biot-Savart law solved problems. Okay, so the question number 1, determine the magnitude of the magnetic field of a wire loop at the center of the circle with radius r and current I. Okay, so the question number 1, we have the wire loop. This one is wire It's called the length of the wire is equal to L. Is equal to L. And the current is carrying in this direction again, I. And we should find the magnetic field. And here the determinant magnetic field of the wire loop at the center of the circle radius R. We have such kind of circle here. Circle. And the radius of circle is equal to R. We should find the magnetic field at the center of the circle here, B. Okay, so we use this equation to find the magnetic field. So B R is equal to mu0 divided by 4 pi integral of I dl sine of theta R divided by R cube. Okay. And here, if the I and dl are the length of the wires constant, is a constant, we don't need to use these ones. We should use only BR is equal to mu0 divided by 4 pi integral of I dl divided by R square. Okay, so if they are the constant, so the equation will be like this: mu0 divided by 4 pi multiplied by I multiplied by L divided by R square. What about the L here? L is equal to what here? L is the length of the circle here. Length of the circle. We have the radius of the circle and we should find the length of the circle, okay? So length of the circle is equal to 2 pi R. So this one is also R, this one is 2 pi R. So I should put the 2 pi I instead of the L. So we have the magnetic field is equal to mu0 divided by 4 pi multiplied by I multiplied by 2 pi R divided by R square. Okay, so these cancelled, these R, and we have only, and pi also cancelled, this pi and 2 also cancelled, is 4, and here the mu0 divided by 2 multiplied by I divided by R here. Here not R square, not R3, here R2, and we have only this R. So the magnetic field is equal to mu0 multiplied by I divided by 2R. If we have the circle here and the magnetic field is equal to mu0 multiplied by I divided by 2R. Okay, as you can see here. So if we have the wire and the current is carrying in this direction, so we have the circle here, which radius is R. So the magnetic field is equal to mu0 multiplied by I divided by 2R. Okay. And the next example. Question number 2. Question number 2. A circular coil of radius 5 multiplied 10 to the minus 2 meter and with 40 turns is carrying a current of 0.25 amps. Determine the magnetic field of the circular coil at the center. Okay. Now we have the number of turns. So, for example, I'm sorry, not for example, we have given that the wire and we have the circular coil, let's call this one, okay? And here number of turns is equal to N is equal to 40. It means that here the 1, 2, 3, 4, not 4, we have the 40 turns here, okay? And the radius of this coil, R is equal to 5 multiplied 10 to the negative 2 meters. It means 5 centimeters are 0.05 meters, okay? And the current is carrying in this direction, I is equal to 0.25 amps. Again, we should find the magnetic field B at the center. Okay. So we again use these equations. B. So let me see the equations. B is equal to mu 0 divided by 4 pi integral of I dl unit vector of R unit vector of R. And here we have the number of turns. It means that length of the coil is equal to N multiplied by 2 PR. Okay. So and also here the I is a constant number, so we should use the only I multiplied by L divided by R squared here. Okay, so B is equal to mu 0 divided by 4 pi multiplied by integral of I number of terms and dl divided by R squared. And the I and R is a constant number, so we rewrite this one is following. B is equal to mu 0 divided by 4 pi multiplied by I and r square here. And instead of the L, we should write here the 2 pi r. Okay, 2 pi r. Yes. So this pi are cancelled, and 2 also, here only 2, and here only 1 r. So P is equal to mu 0 multiplied by number of turns multiplied by I divided by 2r. 2r. Here only 2 pi are cancelled, r mu 0 and okay. Now we will put the numbers instead of these ones. Okay, mu 0 is equal to what? 4 pi multiplied by 10 to the negative 7. And the number of turns is equal to 14. And the current is equal to 0.25 amps divided by 2 multiplied by R. R is equal to 0.05 meters. Okay, so B is equal to 4 multiplied by 3.14 10 to the negative 7 multiplied by 40 multiplied by 0.25 is equal to I think 10. Yes, 10. So 0.05 multiplied by 2, 0.1 only. So 4 multiplied by 3.14 multiplied by 4, 12.56. 12.6. And here the 10 to the minus 7, here 10 to the 1, here also 10 to the minus 1. If 0.1 is going to move here, it should be, and the 10 should be 100. So here we should write 10 to the negative 5. Or just so 126 10 to the minus 6 Tesla, 126 micro Tesla. Let me check the answer. So number of turns is 40, R is equal to 0.05 meters, I 0.25 amps. Should find the B. So B is equal to mu 0 multiplied by N multiplied by I divided by 2R. Okay, this is true. Answer, we have the 1.2 multiplied 10 to the negative 4. It's okay. Okay, now the question number 3. If you want, you can calculate this one, guys. And after, I will check it. Okay? Can you solve? Vladislav, can you solve this one? Determine the magnetic field at the center of the semicircular piece of the wire with a radius 0.2 meters. The current carried by the semicircular piece of the wire is 150 amps. Now we have the semicircular coil, not the circular, okay? So L is different here. And here we should find the L with circular coil is equal to 2 pi r, okay? But with the semicircular, L is equal to only PR, not 2 pi r. So we should use the PR instead of 2 pi r here, okay? Let me clean this part. Okay, this one is circular coil, but we have only semicircular coil like this. Only this, I mean. Okay, and the current is carried in this direction. So this radius R is equal to what? 0.2 meters. And current 150 amps here. We should find the magnetic field at the center of the semicircular piece of wire. Okay. B. So B is equal to mu 0 divided by 4 pi integral of I multiply dl sine of theta again r unit vector divided by r unit vector. Again, we have the current and radius is constant number, so we should use this one. So B is equal to mu 0 divided by 4 pi integral of I dl divided by r squared. And the B is equal to mu 0 divided by 4 pi I divided by r squared. What about the length of the semicircular piece of wire? So length of the semicircular wire is equal to only pi r. If this one is circular wire, the length of the circular wire is equal to 2 pi r. But here the semicircular wire means that we have only pi r. Okay. So pi r cancelled and 1r also cancelled. We have b is equal to mu 0 I divided by 4r. This one. I will put the numbers instead of the mu 0 I and r. So mu 0 is equal to 4 pi multiplied by 10 to the negative 7 multiplied by I 150 amps divided by 4r. R is equal to 0.2 meters. So these two 4 are cancelled and we have only pi multiplied by 100 divided by 150 divided by 0.2. So pi is equal to 3.14 multiplied by 150 divided by 0.2. This is equal to 2355 multiplied by 10 to the negative 7 Tesla, or 235.5 microtesla. This is the final answer. Okay, understand this one, guys? Let me know if you understand this one. Okay, now our last slide is for you as a bonus, okay? During the exam, you will have the one question related to this example. Be careful, okay? So we have a square loop of side L carries a current I. Determine magnetic field at the center of loop. At the center of loop. So the magnetic field is equal to 2 multiply square root of 2 multiply mu 0 multiply current divided by pi L. The final answer is here. The final one is here. Okay, be careful for these exercises. You will have this such kind of such problems during the next exam. Okay. So the bonus problem, bonus question. Okay. You have the circular loop. Each sides are equal to each other. Okay, here. So each side is equal to L, 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 and L. You should find the magnetic field at the center of the loop here, the B. The radius of the circular coil is equal to R, so R is equal to L divided by 2. Okay, and the current is carried in this direction. This is the I. So we have I, we have the radius R, and we have the length of the side of the loop, and we should find the magnetic field at the center of the circular coil. Square loop. So the magnetic field is equal to 2 square root of 2 multiplied by mu 0 multiplied by I, which is current, divided by pi L. Remember these equations, please. This one, okay? So B is equal to 2 multiplied by square root of 2 multiplied mu 0 multiplied by current divided by pi L. For example, the L is equal to, let's say, 2 meters. And the current is equal to 10 amps. Yeah. What about the magnetic field? What about the magnetic field here? So the field is equal to 2 multiplied by square root of 2 mu 0 is 4 pi multiplied 10 to the negative 7 multiplied by current 10 amps divided by pi and L. L is equal to 2 meters here. 2 pi are cancelled. We have only the 2 multiplied by square root of 2. Square root of 2 is equal to 1.43. 1.43 multiplied by 2 multiplied by 4 multiplied by 10 divided by 2. Or just these two also cancelled. We have only these ones. So 1.43 or 41. Let me check. The square root of 2 is equal to what? Square root of 2 is equal to square root of 41, not 43. So, sorry, 1.41. So 1.41 multiplied by 4 multiplied by, not multiplied, just 5.6. Here the 5.6. So 10 to the negative 7 multiplied by 10 is equal to 10 to the negative 6. It's micro. This is the final answer. Okay, that's all, guys. And our next lesson will be next Friday, or this Friday. Yes, our next lesson will be this Friday, the 27th of November, and we will see the exam simulation. Okay, exam sample 2. Can you hear me, guys?
Yeah, we can.
Are you sleeping? Ah, okay. Thank you very much. Please be careful. The three these ones. Okay, the bonus example, and during the exam you will have such kind of problem.
When is the next exam be?
And this one also. Be careful. This one. Okay. Next lesson will be on Friday. Okay.
Okay.
And I couldn't hear you, Dennis. Can you repeat, please?
I had problem with my internet.
And on Friday, we will see the exam simulation. You will solve only problems. I think the 5 or 6 problems. Okay, guys, we will finish our lesson. Okay.
Okay.
And the next lesson will be on Friday, I think, in Baltic Center. Okay, so we will see the exam simulation next lesson, and our next midterm exam will be December, I think. I don't know.
Okay.
Okay, bye bye. See you.
Mm-hmm.
Thank you very much.
Goodbye.
Bye bye.